Hello, everyone. Thank you for coming to this talk. I'm Zicun Cong from Fraser University. This work is collaborated with Lingyang Chu, Yang, and Professor Jian. In this work, we provide an efficient algorithm to compute the most comprehensible counterfactual explanation on Kolmogorov-Smirnov test. The well-known case test is a statistical hypothesis test that checks whether a test set is sampled from the same probability distribution as a reference set. If a reference set and a test set fail the case test, it indicates that the two sets are not likely from the same probability distribution. The case test has been widely used to detect differences, changes, and anomalies in many areas, such as database security and AI systems. Many important decisions are made based on the raised alarms about changes and abnormality. Understanding why a case test is failed can build trust from users and thus improve the decision quality. Let's have a quick review of the case test. Denoted by R and T, the reference set and the test set. They are multi-sets of real numbers. The null hypothesis is that R and T are sampled from the same probability distribution. The case statistic is defined as the largest difference between the cumulative distribution functions of the two sets. If the case statistic is larger than a threshold P, the case test is failed, and thus the null hypothesis is rejected. Here is a toy example. The CDFs of our example test set and reference set are shown in the table. The largest difference between the two CDFs appear at the value of 13. The case statistic is 0.75, which is larger than the threshold P. Thus, the case test is failed. A counterfactual explanation of a failed case test is a smallest subset I of the test set T, such that after removing I from T, R and T can pass the case test at the same significance level. Continue our toy example. After removing I1 from T, we can get T prime. T prime and R can pass the case test. Since I1 is the smallest subset that can reverse the failed case test into a passed one, I1 is a counterfactual explanation. Similarly, if we remove a larger subset, I2 from T, we can also reverse the failed case test. However, I2 is not a counterfactual explanation because I2 have more elements than I1 and is not the smallest subset that can reverse the failed case test. Due to Rashomon effects, multiple counterfactuals may coexist for a failed case test. Simply presenting all counterfactuals not only may overwhelm users, but is also computationally expensive. A desirable idea is to return the most preferred explanations to the users. In our work, users can express their preference as a ranked list of the elements in T. The data points having smaller ranks in L are more preferred by the user. The most comprehensible counterfactual explanation is the one that has the smallest lexicographic order based on L. Continue our toy example. Assume a user provides a ranked list as the one shown here. The element T4 is ranked at the top of L. By definition, the explanation I1 is more preferred to the user than I2. This is because I1 has a smaller lexicographic order than I2 based on the preference list L. A brute force method to find explanations is to enumerate all subsets of the test set and conduct the case test for each subset. However, this method has to check exponential number of subsets. Another way is to train a machine learning model to remove the elements in the test set, such that the case test is reversed. But this method helps to minimize the L0 norm of their perturbations, which is NP hard. One may also try to reverse the failed case test by removing outliers. However, the detected outliers cannot guarantee to reverse the failed case test. In our work, we propose a two-step method which guarantees to efficiently find the most comprehensible counterfactual explanation. In the first step, we try to find the size k of explanations, that is, the number of elements in an explanation. First, let me introduce a concept. A subset is called a qualified subset if it can reverse the failed case test. By definition, a counterfactual explanation is also a qualified subset. To search the size of explanations, we enumerate subset size h from 1 to the cardinality of t minus 1. We call a set of sets h an h subset. For each h, we check if there exists a qualified h subset of t. By definition, the smallest h that has a qualified h subset is exactly the size of explanation. A brute force method to check the existence of qualified h subset has a very poor computational efficiency because it needs to conduct a large number of case tests. To tackle the computational challenge, we develop an efficient algorithm to check the existence of a qualified h subset without conducting case tests. The algorithm only takes linear time with respect to the size of R and T. In our second step, we take the output from the first step and construct the most comprehensible explanation by a greedy algorithm. First, let me introduce a necessary concept. An H subset S is called a partial explanation if there exists an explanation that is a superset of S. Recall that we want to find the explanation with the smallest lexicographic order based on L. Motivated by this objective, we scan the data points in the test set in the order of L and iteratively add selected data items into our constructed explanation I. We guarantee that after adding each selected data item, the subset I is always a partial explanation. Therefore, after adding k data points, the subset I is exactly the most comprehensible explanation. We develop an algorithm which only takes linear time to verify if a subset is a partial explanation. Limited by time, we only show a case study in this video presentation. Please refer to our paper for more experimental results. In this case study, the COVID cases reported in August and September 2020 in the province of British Columbia are used as the reference set and the test set. Each reported case in the two sets is associated with the age group of the patient. A failed case test between the two sets suggests that the infected cases in those 2 months are not likely to follow the same distribution on age groups. Figure 1 shows the histogram of the two sets. We sort the reported cases into a preference list, L, in the population descending order of the reported area. Our generated explanation only includes cases from the area with the largest population. Therefore, it best matches users' preference. Figure 2 shows the histogram of our explanation. Our method mainly selects the data points from age groups that have larger relative frequencies in the test set than in the reference set. In summary, concept-wise, we propose the notion of most comprehensible counterfactual explanation on case test. Computation-wise, we develop an efficient algorithm to find the most comprehensible explanation. Experiment-wise, we present a systematic empirical study to verify the effectiveness, efficiency, and scalability of our method. Thank you very much for listening.